Welcome. This is Module 4, Topic 1, Lesson 4, a simulating conversation. In this activity or lesson, we're going to be simulating simple experiments. And we're starting with activity 4.1, simulating baby births. Let's get started. What percent of babies born at a certain hospital are female? One way to answer the question is to perform a simulation. We've got that vocabulary word coming up, so get your pencils ready. A simulation, say simulation, is an experiment that models a real world situation. So, again, a simulation is an experiment that models a real world situation. When conducting a simulation, you must choose a model that has the same probability of the event. So, let's think about how we might do that. Question number 1 says, what model might be appropriate for creating a simulation of this event? Number 2, describe the sample space for this situation. Number 3, what is the event that you are trying to determine? And number 4, suppose the probability of a family having a female baby is 1/2. What percent of babies born at the hospital would you expect to be female? So, in a second, you are going to actually answer these questions 1 through 4 on your own or with a partner first, being that now we're familiar with probability, the vocabulary behind it, and determining outcomes. This is what I should expect to see on your papers. So for number 1, what model might be appropriate? You can draw a picture or you can simply write it out. I'll give an example to start. So if we're talking about babies being born at a hospital, there are only 2 possibilities, male or female. So that could potentially look like a coin toss. This is just one example, and I want you to give your own examples. So it could look like a coin toss where I've got 1 heads and 1 tails. Now I'm not going to draw heads and tails because I don't know how to draw that, but you can see one side is one thing and the other side is the other. Or that could even represent 2 color counters where one side is dark red and the other side is light yellow. Number 2, actually before I move on, I want you to try to get 2 more models in, at least 2 more. Number 2 says describe the sample space. Remember, sample space we put in these braces, and that's just our outcomes, possible outcomes. Number 3, what is the event that you're trying to determine? So, what is the probability of what? What are you trying to determine? And also, number 4, what is the percentage? So, the theoretical probability in percent form. Alrighty, I'm going to pause this there. And I want you to answer questions 1 through 4 on your own or with a partner. Set a timer for 3 minutes max. Maximum 3 minutes. Pause here. Alrighty, now that you've had time to work, let's compare answers. So for number 1, it says what model might be appropriate for creating the simulation. So we talked about a coin toss or a 2-color counter because there are 2 possible outcomes. You could have also said a spinner. And if you're going to use a spinner, think about how many sections would that spinner need to be split into. 2, of course, because for this simulation, there needs to be 2 possible outcomes. I even put a dice might be a good simulation, where as one outcome would be even numbers and the other outcome would result in odd numbers. So that also could be used as a simulation. And if you got anything else, such as pulling a name out of a hat, or a result out of a hat, marbles in a bag, as long as it results in 2 possible outcomes, it is correct. Number 2 says describe the sample space. Remember, that's just all of the possible outcomes listed in those braces. which are for here in this situation, girl or boy. Number 3, what is the event that you're trying to determine? Well, they gave us that in the very first sentence. What percent of babies born at a certain hospital are female? So the event that we're trying to determine is what is the probability of our baby being born girl or female. And number 4, what is the percentage if the probability is 1/2? We all know 1/2, or should know, that 1/2 is equivalent to 50%. So the probability, the theoretical probability, is 50%. All right, let's move forward. So it says, let's use the toss of a coin as a model. Heads will represent the birth of a female, and tails will represent the birth of a male. So now we're about to conduct a simulation. Except our simulation is going to be slightly different, being that we are doing this online. We have access to other tools. So, what we'll be using is a digital coin that I've actually been able to change to girl and boy, which you will see in a second. Number 5 says, if you toss a coin twice, list all the possible outcomes from this simulation. Well, one way we can notate 2 coin tosses is by putting that simulation in parentheses. So, if I were to toss the coin, a possible outcome could be I toss girl, and then on my second, I flip boy. And actually, let me just write a 1 and a 2 underneath so that makes more visual sense. My first coin flip could be girl. My second coin flip could be boy. But it says list all of the possible outcomes. If I were to toss a coin twice, it also could be girl, girl. My first coin flip, my second coin flip. Go ahead on your own, take a couple seconds, so no need to pause, but take a couple seconds and fill in what would the possible outcomes be if I were to, or let me say this, what would the other outcomes be if I were to flip this coin twice? I hope that was enough time to fill in 4 quick letters, but those other outcomes could potentially be boy, girl, where you're flipping boy first, or even boy, boy. All right, let's continue. So number 6 is toss your coin 2 times, and then we're answering how many of the coin tosses resulted in heads. And remember, in this simulation, we're changing things slightly. So we're not talking about heads and tails. We're talking about girl and boy. So that actually is asking how many coin tosses resulted in girl, or your female result. Part B says, according to your simulation, what is the experimental probability? So the probability experimental, so what result we get of our female being born. So let's go ahead and do this. We're going to toss our coin 2 times, and then we're going to get that experimental probability. So here is our coin. Let's go ahead and flip. All right, we've got boy. And I'm going to note that with the tally mark off to the side so that I can keep track. And then our second flip is girl. So in pink, I'm going to notate girl. Now I can answer these questions. How many of the tosses resulted in a girl result? Well, 1 out of 2 resulted in girl. So that was, actually, let me just go to B. So according to our simulation, what is the experimental probability? So the experimental probability was 1 out of 2. Or I guess I should have answered this question as 1, just 1. Now, part C, we're going to skip for now, and I'll explain that afterwards. But let's go to question 7 now. We are tossing our coin 8 times. And then we're going to answer those same questions. How many of the coin tosses resulted in not heads, but getting a girl result? And also, what is the experimental probability of it being female? All right, so let's toss our coin. Let me get my tallies ready. Boy, girl. Okay. So that's 1 for girl, 1 for boy, 2 for boy, and 3 for boy. So I'm going to go ahead and pause here. I know I got 1, 2, 3, and 1 for girls. All right, I hope we've got these tallies down. Let's continue our simulation. 4 more flips. Girl, boy, boy, girl. Okay, so 2 of each. 1, 2, and 1, 2. Well, actually, let me make this a little bit better. 1, 2, 3, 4, 5. There we go. Okay, so now we can answer these questions. How many tosses resulted in girl? So 3 coin tosses resulted in girl. And so then our experimental probability would be 3 out of 8, which was our total coin toss count. Now, part C, I'll go back to. We're not going to complete this because this is an activity that requires you to have different results from your classmates and then to share those results, but I'm going to explain it. So it says share your results with your classmates, then create a dot plot of the experimental probabilities. Did everyone end up with the same results as the theoretical probability of a female being born? Now, you'll see that no, not everyone will have the theoretical probability, which was 1/2. We did, so we would put our, so we would put our dot above 1/2, but there are going to be some groups that got the same as us, and there are going to be some groups that maybe got both boys. So the probability of rolling female for them was 0. And then you're going to have some groups that got girl on both. So that would result in 100% probability, 2 out of 2. And then for 7C, you'll see our numbers are a little bit different, right? We got 3/8 is our experimental probability, which is slightly below 1/2. So it'd be somewhere around here if I were to guess. Or let me not guess. Let me actually do this correct because there is a way that I can figure out. If it's in fourths, I can cut it into eighths. So I'm just going to split each of these sections into halves. And then I can see that I've got 1, 2, 3, 4, 5, 6, 7, 8 sections. So I know that our 3/8 would be right here. Now, some of our groups may have 3/8. Some of your classmates may get 4/8. Some classmates may get 2/8. But as you get more different results, you would see the different possibilities of the experimental probabilities that they got. And now the last question in part C says, how do these results compare to the results in question 6? Well, the main thing that you'll notice and that you'll see is that for question 6, there were only 1, 2, 3 different probability outcomes that they could have received or that they could have gotten. Whereas when you toss the coin more times, then there's a chance that you could get all different types of probabilities. So 1/8, 2/8, 3/8, 4/8. So everyone would have different results. Whereas Here, a lot of us had the same results. All right, moving forward. Question number 8 says, now conduct 50 trials of the simulation. Record the results in the table using tally marks. And then also we're going to note our total and then that total as a percentage. And being that we're not doing this individually but together, we are going to skip number 9. We're not going to create that dot plot with multiple points of data. But after we conduct this experiment, we will answer number 10, or you will answer number 10 on your own, which says, what can you conclude about the experimental probability of an event and its theoretical probability as the number of trials of the simulation increases? So let's go back. We're now going to conduct 50 trials. Now, on screen, we're not going to do all 50 trials, but we're going to do a couple first so you can see how we would flip the coin, put our results in the table, and then continue with our simulation so that in case that you do this on your own one day. All right, so let's go ahead and start flipping. So we've got girl, boy, girl, and girl. So I'm going to go ahead and tally those. We've got, oops, let me change this. Heads is girl, tails is boy. So we had 1, 2, 3 for girl and 1 for boy. Now I'm going to go ahead and continue this simulation and I will show you my results when I'm finished. Alrighty, I am back. I've got my results and I'm going to let you see the results. So after flipping our coin 50 times, the great thing about technology is it keeps track for me. So I'm going to click stats. I don't know why I'm stumbling over my words. And it shows me out of 50 total flips, the result was blue boy 23 times and pink 27 times. So now I'm going to put that into my table. So 23 for boys, 27 for girls. I'm actually going to skip the tally marks and just go ahead and put that total in. So 27 and 23. And the way we find that percentage is by first figuring out what that fraction is. So 27 out of 50 and then 23 out of 50. The great thing about using 50 as a denominator is I can easily just double that to get my percentage out of 100. So out of 100, 27 times 2 gives me 54. So that would mean 54%. And then for my boys, that would be 46 out of 100, which is 46%. All right, let's move on. So number 9, share results with your classmates and create a dot plot. Now, we don't have multiple sets of data. However, you're probably thinking, well, if we were to do this in a classroom setting, everyone's going to have a different number because we just conducted 50 trials and not everyone is going to have these same percentages. That is true. One way we can also estimate on our dot plot or on our probability scale is by percentages. So we know that 1/4, 1/2, 3/4 are all percentage, or not, excuse me, are all benchmark percentages. So from 0 to 100%. And also, if you don't know what these 1/4, 1/2, and 3/4 are as percentages, think of quarters, right? How many quarters make a dollar? 4. So 1/4 would give me 25 cents or 25%. 2/4, 1/2 would give me 50 cents or 50%. And then 3 would give me 75. And then we can estimate where our numbers fall on that scale a little bit easier. So our numbers We wanted to predict the probability of our coin choosing female was 54%. So that's laying somewhere around here. Now, if we did have multiple sets of data, you might notice that your dot plot might look something like this, potentially, where we're just estimating where those percentages are. You might have one outlier over here, you might have one outlier over here, but the majority would go right around the center. And you will know exactly why in about a second. All right, but now I want you to answer this question. What can you conclude about the experimental probability of an event and its theoretical probability as the number of trials increased? So remember our theoretical probability. So probability theoretical, what we thought would happen was 1/2 or 50%. And then what actually happened, I'll use pink. In the first trial, we got 1/2, we did. In the second trial, out of 8, we got a little bit less than 1/2. And in that last trial, we got about a little bit more. I'll write it as a percentage. A little bit more than 1/2. So think about, what do you notice? What do you see? Take about 1 minute to pause here, write your conclusion, and discuss with a partner. 1 minute, pause here. Now, I really wish I could hear all of your answers, all of your awesome conclusions. However, I am but in a computer screen. So let's go ahead and sum up this activity by reading what's below. So it says, using simulations to generate experimental probability is very useful in estimating the probability of an event for which the theoretical probability is difficult or impossible to calculate. As you have investigated, and this is the key here, as you have investigated, the experimental probability of an event approaches the theoretical probability when the number of trials increase. So basically what that's saying is the more trials that you conduct, the closer you get to the theoretical probability. So for example, when we conducted our second trial, we got 3/8. And as a percentage, that is about, just so that we can compare, that is about 38%, which is way less than that 54% that we got when we conducted 50 trials. Another thing that I want you to see is on this awesome coin flip simulator, you can also see global stats. So if I click global stats, I can see how many total times that this coin has been flipped around the world. So it's been flipped so far a total about 63 million times. And look at those percentages. The pink is about 50%, 50.5%, and the blue is at 49.48%. So as you can see, the more simulations that happen, again, the closer our experimental probability is going to reach our theoretical, or be as close to our theoretical probability as possible. Alrighty. That concludes the learning for this activity. I hope you learned something. Awesome job today. I will see you in the next video.